So one little note, I do have a bit of a head cold today, so I've been sniffling and have kind of a scratchy throat. So I think we're gonna bump section 2.5 to next class and just cover 2.4 today, or uh, cover most of 2.4. There's a little section at the end of 2.4 in prime numbers, which fits much better with 2.5. So we're just covering that with 2.5. Um, okay, so the plan for today is just to go through 2.4, finding multiples and factors of a number. And the quote of the day for today, or really idea of the day, kind of two related ideas, but both related to making strategic use of your time that you spend learning material. So I know that we haven't, talked about graphing and curves and so on, but I think a lot of people have heard of kind of the learning curve, and the idea is something like this, that if you look at the relationship between time and knowledge, time spent studying or learning a subject versus knowledge or expertise gained in that subject. When you
Hello.
first start,
I just joined back.
okay, that's fine. Yeah, if you come in or leave, you don't, that's fine. Yeah. So the first bit of time spent learning a subject, you gain a lot of knowledge. The next proportion of time, you gain more knowledge, but not at quite the same rate. The next amount of time that you spend, you're still increasing in knowledge, but the yield is a little bit less. So for instance, to become, a top world expert in a particular field, to get your knowledge really high takes an enormous amount of time, because at some point after you're really, really good at a subject, you need to spend so much time learning to just get a little bit more knowledge about that subject, that the payoff is really decreases quickly. So if you want to be like the world authority on some particular thing, you need to spend an enormous amount of time and almost devote like your entire life to that thing, because the payoff gets so little after a while. But can you spend, a moderate amount of time on a thing and be better than, like, say, better than average, or be better than 75% of people at that thing? That's very achievable, right? So should we spend a ton of time learning one very specific thing, or if we spread ourselves out a little bit and kind of become a jack of all trades, that gets a little bit of a, people say, oh, a jack of all trades is a master of none. Yeah, but if you can do like a whole bunch of trades pretty well, then most people would say that that's a lot more valuable than being able to do one thing extremely well. And if that one thing goes out of style, then you don't have anything to fall back on. Um, So can you make strategic use of the learning curve? Can you say, this is a field that I want to go into, and I realized that by picking kind of ancillary or somewhat related topics to that field, putting a little bit of time in on each of those topics, that can really boost my knowledge related to that field quite a bit, because I can, kind of take advantage of this like beginner increase in knowledge that increases very rapidly, and maybe be better than, you know, better than average, better than 50% of people or whatever. And maybe that puts me above other applicants for the position, that they see that I have this breadth of knowledge as well as the ability to go deep in one particular area. And I think this is related to an idea that I've kind of come up with as the kind of my model for knowledge, is that there are kind of two facets of knowledge that I tend to look at, whether I want to spend my time there or not. And one has to do with what I kind of call the time constant. It's a question of, if I learn something, how long is that good for? How long until that knowledge is obsolete? So we kind of have dynamic versus static. So dynamic knowledge is something you learn, and a week, a month, a year later, it's basically useless. A good example is like sports information. Everybody, you watch the football game and everybody talks about this play or that play at the water cooler this week. But if you say, if you wait a month and you start talking to your buddy and you're like, oh yeah, I remember that play from like 4 weeks ago, they're like, what are you talking about, right? That the value of that knowledge goes to zero very quickly. Um, on the other hand, if you learn something in math, like how to find multiples and factors of a number, like that piece of information is the same a month from now, a year from now, 10 years from now. That's something that's not going to change. And on the other axis, I have the type of knowledge, whether it's trivial or foundational. Trivial knowledge is kind of like it sounds trivia. So these are like isolated little islands of knowledge. I learned one fact about one particular thing, and I can't really relate it to anything else in my mental model. Um, it doesn't really, help me investigate anything else, to a deeper level. I can't really build off of it. It doesn't really relate to too much else. Versus foundational, where if I learn this piece of knowledge, I can attach it to other pieces of knowledge that I already know. That might give me a different perspective or a deeper understanding of those other pieces of knowledge that I already have. And it gives me a stepping stone that I can build off of to move on to other things. So I like to spend my time here as a math guy. That's kind of right. I mean, same kind of thing. Like we're talking about multiples and factors, then we're going to build off of that and talk about prime numbers and factorizations. And we're going to build off of that and talk about how to add and subtract fractions. That's where all of this is going. But that's not to say that, just because I like this quadrant, that this is the only good quadrant to be in. For instance, IT support. Um, is very much in the dynamic and trivial uh, quadrant, but we definitely have need for IT support folks, right? If another instance of Word comes out, another update comes out, and they move some things around, and the IT person has to spend time relearning stuff that they already knew. Last version, they knew where all this stuff was. We get an update, now they got to relearn where that stuff is. Um, and then when there's another update, it's going to be, they're going to have to relearn it again. So you kind of spend a lot of time just keeping up to date on things. And some people really like those kind of challenges. Tax is another area. So like tax law, the tax rules change every year. So accountants are spending a lot of time keeping up with the new rules and all of that. And some people like that challenge, and some people don't like the fact that they have to relearn things that they've already learned, 20 times through their career. So just thinking in terms of what career are you looking at going into, what are the kind of quadrants of knowledge that it's going to really push you into, and does that kind of mesh with your way of thinking or not? Like it would drive me crazy to be a tax professional who I'm like, I just learned this thing 2 years ago and last year, and now I need to learn it again, like because they've changed it a little bit. That would drive me crazy. But there are some people who like that challenge. And there are some people who, would get bored as heck learning all of these things that never change. And it's just like, okay, I know that. And now I never have to really keep up with it. So that's the thought for today. And as I mentioned, today's plan, 2.4, finding multiples and factors. We're going to bump prime factorizations and least common multiples to next time. And we're also going to bump the last tiny bit. Again, I don't know why they do this in the book, but they have prime and composite numbers at the end of 2.4. I think it probably meshes a little better with the material 2.5. So we're going to bump that to 2.5 next class as well. Okay, so we're going to start with a definition. A multiple of the number is the product of that number and a natural number or a counting number, a number like 1, 2, 3, etc. So a couple examples. We can say find 5 multiples of 3. So if I take 3 times some counting number, some natural number, I could take 1, for instance. 3 times 1 is 3. So actually, a number is a multiple of itself. I could have like 3 times 7, that's 21. 7 is a counting number. I multiply it by 3, it's going to be a multiple of 3. So I would say that 21 is also a multiple of 3. Maybe 3 times 10, 30. 30 is a multiple of 3 as well. I could do like 3 times 3. There's no reason I can't multiply a number by itself if the number I start with is a counting number. So 3 times 3 is 9. 9 is a multiple of 3 because it's the product of 3 and some counting number, some natural number that just also happens to be the number 3. Or I could have, let's say 3 times 5, 15. 15 is also a multiple of 3. And in fact, if I look at my times table, if I look at the, say, row corresponding to 3 in my times tables, I have 3 times 1 is 3, 3 times 2 is 6, 9, 12, 15, 18, 21, 24, although it looks like a 29, 24, 27, and 30. These are actually all multiples of 3. So here are 10 different multiples of 3. So if I look at a specific, say, row in my times tables corresponding to, for instance, 3, I can find a bunch of multiples of 3 right away. Or if you preferred, you could look at the column, which will have the same information, 3, 6, 9, 12, and so on, going down the column. So if I want to find a certain number of multiples of a given number, maybe an easy way to do that is just to start by going across my times table in that row. If I want to find 6 multiples of 7, if I want to find 6 multiples of 7, maybe I just do 7 times 1, 7 times 2, up through 7 times 6. That would be kind of the easiest way to go about this. And again, if I'm pretty familiar with my times table at this point, this shouldn't be too bad of an exercise. Now, if I want to find multiples of a bigger number, like, find 3 multiples of 17, I can take a similar approach. Just multiplying by, say, 1, 2, 3. I don't have a row or column in my times tables for 17. So I need to do these each kind of the long way. Well, 17 times 1 is 17. That's an easy one. But 17 times 2, 2 sevens are 14, carry the 1. 2 times 1 is 2, plus 1 is 3, 34. And then 17 times 3, 3 sevens are 21. 3 times 1 is 3, plus 2 is 5, 51. So if I had a bigger number that I wanted to find multiples of, I could come up with a couple multiplications that I want to do, and then just go off to the side and work them out as needed. So if I want to find several multiples of a number, this is how I might go about it. Or I could look at it kind of from the opposite direction, that a number is a multiple of another number if it's the product of the other number and a natural number or a counting number. In other words, I might ask a question like, is 42 a multiple of 7? And my answer here will be yes. For this first one, yes. I do see it in my list of multiples, so it's definitely a multiple of 7. 7 times 6 equals 42. A number, say 42, is a multiple of another number, 7, if it's the product of 7 and a natural number. 7 times 6 is 42, so yes. Is 16 a multiple of 3? Well, if I look at my multiples of 3, I see numbers like 3, 6, 9, 12, 15, 18, and then they just keep getting bigger. So I've passed up 16, and I don't see it in my list. So I see that 3 times 5 is 15, 3 times 6 is 18. There are no multiples of 3 between 15 and 18 because there are no natural numbers between 5 and 6. If I keep going this direction, my numbers just get bigger than 18, or this direction, they get smaller than 15. So 16 is not a multiple of 3. No, because if I did, 16 times n equals 3, there's no natural number n I can put in there. Oops, other way around. 16 equals n times 3. There's no natural number I can put in there to make this a true equation. If I try n equals 5, that gets close, but I get 16 equals 15. That doesn't work. If I try n equals 6, again, pretty close. 16 equals 18, but that's not true either. So is 16 a multiple of 3? No, it's not. So for each of the following numbers, let's determine whether it's a multiple of 2, whether it's a multiple of 5, and whether it's a multiple of 10. So to help us with this, let's look for some patterns. If I look at my kind of 2 times table row, 2 times 1 is 2, 2 times 2 is 4, 6, 8, 10. So 2 times 5 is 10. 2 times 6 is 12, 14, 16, 18. For 2 times 9, 2 times 10 would be 20. And if we wanted to keep going, 2 times 11, 22, 24, 26, 28, 30, we might see a pattern repeating over and over again. We might see that we have this pattern in the last digit, 24680, 24680, 24680. And that repeats over and over again. So it kind of seems like all all multiples of 2 end in 2468 or 0. And it also kind of seems like any number that ends in 2468 or 0 is a multiple of 2. If I try to find one, a number that ends in 2468 or 0 that's not a multiple of 2, seems like it's going to be hard to find because, if it's between, strictly between, greater than or equal to 10, less than 20, this is all of the numbers between 10 and 20 that end in 0, 2, 4, 6, or 8. It's between 20 and 30. Here are all of those. So it seems like a number is a multiple of 2 if and only if it ends in 2, 4, 6, 8, or 0. If we look at the 5 times tables, 5 times 1 is 5, 5 times 2 is 10, 15, 20, 25, 30, 35, 40, 45. That takes us up to 9 times 5. And I see a kind of similar structure that these numbers all end in either 5 or 0. So all multiples of 5 end in either 5 or 0. And we can say the reverse as well in this case. We can say that any number that ends in 5 or 0 is a multiple of 5. Maybe I should say any natural number ending in 5 or 0 is a multiple of 5. And then if we look at our multiples of 10, if we look at our 10 times table, It might not be on the times table that we have, but we know that 10 times 1 is 10, 10 times 2 is 20, 30, 40, 50, and so on. So numbers that end in 0 are multiples of 10. So I can come over here and just look at each of these numbers' last digit and actually tell very quickly, just by what that last digit is, whether or not it's a multiple of 2, 5, and or 10. So 452 does not end in a 0. It's not a multiple of 10. It does not end in a 5 or a 0. It's not a multiple of 5. It does end in a 2, 4, 6, 8, or 0. It ends in a 2, so it's a multiple of 2, but not 5 or 10. 535, it does not end in 2, 4, 6, 8, or 0. It's not a multiple of 2. It does end in 5 or 0, so it is a multiple of 5. It does not end in 0, so it's not a multiple of 10. It's a multiple of 5, but not 2 or 10. 723 ends in 3. It does not end in 2, 4, 6, 8, or 0, so not a multiple of 2. It does not end in 5 or 0, not a multiple of 5. Does not end in 0, not a multiple of 10. So not a multiple of 2, 5, or 10. Not a multiple of any of these three numbers that we're looking at. 1,240, big number, but again, we're just looking at that last digit, that's 0. It does end in 2, 4, 6, 8, or 0. It does end in 5 or 0. And does also end in 0. So it is a multiple of all three. Multiple of 2, 5, and 10. And then lastly, 125 does not end in 2, 4, 6, 8, or 0, so it's not a multiple of 2. It does end in 5, so it's a multiple of 5. And it does not end in 0, so it's not a multiple of 10. And maybe to make these a little easier for you to read, I'll circle in green the ones that it is a multiple of. Okay, so let's look at another example here. For each of the following numbers, determine whether it's a multiple of 3. We could write out our 3 times table. 3 times 1 is 3, 6, 9, 12, 15, 18, 21, 24, 27. Unfortunately here, I kind of see that the last number just is changing all the time. I don't really see a discernible pattern. It's pretty hard to find a pattern for the threes, but it turns out that there is a pattern that if the sum of the digits of a number is a multiple of 3, then the number is a multiple of 3. So I can see easily that say 3, 6, and 9 are multiples of 3. Those are easy for me to tell. 3 times 1, 3 times 2, 3 times 3. I can just kind of figure that out. If I look at, say, 12, that's a little harder, but 1 plus 2 equals 3. 3 is a multiple of 3, therefore 12 is. If I look at 15, 1 plus 5 equals 6, and I can see really easily that 6 is a multiple of 3, therefore 15 is. 18, Again, maybe I don't see immediately that that's 3 times 6, but 1 plus 8 is 9, and I do immediately see that 9 is a multiple of 3, so therefore 18 is a multiple of 3. Uh, so what about a harder number like, and I can see the same for these 20s as well. 2 plus 1, 2 plus 4, 2 plus 7, 3, 6, and 9 again. What about a harder number like, say, 753? I don't know right away whether this is a multiple of 3. It's too big of a number. I mean, I could start trying numbers like, what's 3 times 100? Well, that's 300. I need to go bigger. What's 3 times 200? That's 600. I'm getting closer. What's 3 times 300? That's 900. I overshot. So I need to pick a number between 200 and 300. What's 3 times 250? That's, 750. I'm getting pretty close. I might be able to work it out that way just by kind of trial and error. But you can, I think, see that this is a pretty tedious process, especially if it's a, you know, more complicated, if it's a larger number, like say even 1800 instead of 750 or so. I don't want to just really resort to trial and error, just guessing a bunch of numbers and seeing whether that ends up, making a multiple of 3 that is the number that I'm looking for. On one hand, if my number is a multiple of 3, I will probably eventually find it that way, but it's pretty inefficient. If my number is not a multiple of 3, I'm not going to be able to find my number that I'm looking for by just picking multiples of 3. So I might spin my wheels for quite a while before I convince myself that it's not a multiple of 3. And again, I want something a little more efficient. So I'm going to use this test, this rule, or this property of the multiples of 3 on 753. Again, it's a big enough number that I don't just know right away whether it is or is not. So I add its digits. 7 plus 5 is 12, plus 3 is 15. And 15 is a multiple of 3. It's 3 times 5. Since the sum of the digits is a multiple of 3, 753 is a multiple of 3. And in fact, it's 3 times 251. I might have been able to see that 3 times 250 gets me pretty close. 3 times 250 is 750. Then I just need one extra 3 on top of there to make 753. If I look at 323, again, I might be able to guess and check my way to get a number that's pretty close and convince myself one way or another, but probably going to be pretty tedious. It's also probably going to be pretty error prone, right? If I have to do a whole bunch of multiplications, the chance that I mess up one or two of those and throw my answer off is pretty good. But I have a better process, so I'll add the digits together. 3 plus 2 plus 3. That gives me 8, not a multiple of 3. So therefore, 323 is also not a multiple of 3 because the sum of its digits is not a multiple of 3. We can see that, for instance, 3 times 100 gives me 300. 3 times 107 would give me 321. And 3 times 108 would give me 324. So between 107 and 108 as my multiple of 3, I jumped from 321 to 324. I jumped over 323. But we don't have to even go that extra step because we just used this property to verify that it's that because the sum of the digits is not a multiple of 3, this number 323 is not a multiple of 3. So what about 1,872? Again, looking at it, I don't know whether it's a multiple of 3. I could try a bunch of guess and checks, probably going to be tedious and error prone. But if I come over and add the digits together, so 7 and 8 is 15, plus 3 is 18. And one thing to note is you might immediately recognize that 18 is 3 times 6, but if you didn't, so really the question is this a multiple of 3? But that's the same question that I'm asking over here. If I add my digits together and I still get a big number, I'm just asking the same question about that big number, but that's quite a bit smaller than the one I started with. I can do 1 plus 8 equals 9, which I see is 3 times 3. So again, I ask, is this a multiple of 3? Yes, this is. 9 is a multiple of 3. Therefore, 18 is a multiple of 3. Therefore, 1,872 is a multiple of 3. Is 64 a multiple of 3? 6 plus 4 equals 10. And 10 is not a multiple of 3. I know 3 times 3 is 9, and 3 times 4 is 12. I've skipped over 10. So no, 64 is not a multiple of 3. But again, if I had some, enormous number, like this, I don't know if this is a multiple of 3 or not. But if this is the number I was looking at, if I'm asking, is this number a multiple of 3, I add the digits together. When I'm adding a bunch of digits like this, sometimes it's helpful to group them. 7 plus 3 is 10. 8 plus 2 is 10. 6 and 5 is 11 plus 1 is 12. So I have 12 plus 2 tens. So that's 32. And I'm asking, is this a multiple of 3? This is still kind of a big number. So then I just repeat the process. And I see that 5 is not a multiple of 3. 3 times 2 is 6. 3 times 3 is 9. I've skipped over the 5. Therefore, 32 is not a multiple of 3. And therefore, this enormous number at the beginning is not a multiple of 3. Even with just 2 steps, you see that I got down to a very manageable number very quickly. So this is a pretty nice test. We can take a really big number within 1, 2, maybe 3 steps for an absolutely enormous number. We'll have figured out whether it's a multiple of 3 or not. Okay, so the ideas of divisibility and divisibility tests, we've already pretty much described these ideas with the examples that we just did. So if we want to carefully define divisibility, we would say that a number m is a multiple of n. If that's true, then m is divisible by n. So if m is a multiple of n, if m equals n times some natural number, then we say that m is divisible by n. Some common divisibility tests, well, the ones we saw above, divisibility by 2, 5, or 10, those are the ones that look at just the last digit. And in the case of 2, divisibility by 2, we're looking for 0, 2, 4, 6, or 8. Or in other words, if the last digit is an even number, then the whole number is an even number. That's another way to say it. Divisibility by 5 and 10, we're looking for either the last digit being 0 or 5, in the case of divisibility by 5, or looking for that last digit to be 0 in the case of divisibility by 10. And then we had the little bit more complicated divisibility by 3, where we add up the individual digits and ask, is that divisible by 3? Probably not a pattern that we would have, immediately recognized based on the 3 times table here. But it is a pattern that holds, and it can be proven that it holds for arbitrarily large numbers. So we kind of verified it for these ones over here, but we didn't really prove or really argue systematically why it should be true for numbers bigger than these ones. Maybe once we get up to 1,000, it stops working or something. How do we know that it won't? It turns out that it won't. We can prove it works for any number. But that's a bit beyond the scope of this course. We can also make new divisibility rules from existing divisibility rules. So for instance, a new one down here is a number is divisible by 6 if it is divisible by both 2 and 3. Why would that be the case? Let's just investigate this one, because that's kind of the new one that we came up with. Well, remember, m is divisible by n means m is a multiple of n. So n divisible by 6, or let me call it m so that I'm consistent with the notation above. M is divisible by 6 means m equals, let's say 6 times k. I don't want to use n because we have n in a different context up there. But 6 is 2 times 3, right? So 6 times k is 2 times 3 times k. Here, k is some natural number, a number like 1, 2, 3, something like that. But m is divisible by 2 if it is 2 times some natural number. Well, if I take a natural number and I triple it, it's still a natural number. So m is 2 times 3k. So it's got to be divisible by 2. I have my associative property of multiplication coming in here saying that I can kind of put the 3k together and I have 2 times 3k. And on the other hand, I could leverage my commutative property. 2 times 3 times k, I could write as 3 times 2 times k, or 3 times 2k like this. This is 3 times, well, a natural number times 2. If I double a natural number, it's still a natural number. 7 times 2 is 14, something like that. M is also 3 times a natural number. It's divisible by 3. So if I want to know if a number is divisible by 6, I can check that it's divisible by both 2 and 3. Or if I wanted to know, say, I don't know, if a number is divisible by 30, I could check that it's divisible by 10 and divisible by 3, because 30 is 3 times 10, right? So if I had say a 30 here instead, I could think of that as 3 times 10 times k. So I just check my divisibility rules for both 3 and 10. So we can make new divisibility rules off of current ones. There are some divisibility rules we've skipped over here. There are rules for 7 and 11 that exist, but they're actually kind of quite complicated and cumbersome. So for 7 and 11, maybe the best approach is something along the lines of the trial and error method. The 7 and 11 methods are cumbersome. They're also kind of easy to get messed up. They have kind of additions and subtractions, and it's easy to get things backwards or forget exactly how it works. So maybe for those, because the complexity of the general method is so high, at least if the number isn't super huge, maybe it's worth it to just do trial and error and just be really careful with our calculations, right? So we're always balancing complexity of the solution method with amount of work, right? Usually if we increase complexity a little bit, we can decrease the amount of work we have to do by quite a bit, but sometimes we have to increase the complexity so much relative to the decrease in the amount of work we do that maybe it's not worth it. Maybe it's better using a simpler method. It might not be the most elegant method, but gets you the answer in a more reliable, dependable way. And this is, a trade-off that I think I think probably just about every career faces. That there are more complex approaches that have some benefits, but sometimes the difficulty of the complexity outweighs the benefits. Certainly in like computer science, right? You can write a big complicated program to do something very quickly in the computer, but like if it took you an hour to write the program and your computation time went from 3 seconds to 1 second, like, you know, I spent an hour of my time to save 2 seconds of computer time. I'd rather just, even if it took an hour of computer time, I could just hit enter and go to sleep and wake up the next day and the computer will have figured out the answer, right? It's um, my time is much more valuable than computer time. At least I think so anyway. Um, so there is always a bit of a trade-off there, but these are rules where the trade-off is almost always in favor of the more general rule. And like I said, of course, you don't have to be an automaton. You can make the decision that, if I ask, is, is 10 a multiple of 5? Well, that's a small enough number you just guess and check. Yeah, it's 5 times 2. Or is 35 a multiple of 5? Yeah, it's 5 times 7, right? So you can make an educated decision as to how big the number ought to be before you don't want to do the guess and check and want to do the general method. Okay, so when we say factors, remember that, let me split this off here a little bit. When we say factors, remember that factor times factor equals product. So when we're talking about factors, we're talking about things that are multiplied together to get a product. So if I use the word in this context, find all factors of 42, really what I mean is find all numbers that 42 is divisible by. In particular, find all natural numbers, find all counting numbers that 42 is divisible by. That's really what we're kind of asking here. We kind of say it in this way, find all factors of 42, but really we mean find all counting numbers that 42 is divisible by. So let me start out with what's my first possible factor? Well, 1, it's the first counting number. So these are candidate factors. Is there something I can multiply by to get 42? OneNote just loves making my 4s into 9s. I should try to be more cognizant when I'm making these problems about avoiding 4s in my problems. I don't know. I seem to use the number 4 an awful lot. Or maybe that's just confirmation bias because OneNote turns my 4s into 9s, so I recognize it each time I have a 4 in there. But I do see that 1 times 42 equals 42. So 1 is indeed a factor of 42 because 1 times 42 is 42. Is 2 a factor of 42? Is 42 a multiple of 2? Or is 42 divisible by 2? We could say it that way. I know that 42 ends in a 2. By my divisibility rule for 2, yes. So I could either just check it off by the divisibility rule, or I could recognize that it's 2 times 21. It gives me 42. What about 3? is 42 divisible by 3? If I take the sum of the digits, 4 plus 2, that gives me 6. 6 is divisible by 3. It's 2 times 3. So yes, by divisibility rule. If I wanted to go a little further, I could ask 3 times what gives me 42 then? Well, 3 times 10 gives me 30. 3 times 15 gives me 30 plus another half. I might think of it that way. Gives me 45. Maybe 3 times 14. So I could do a little bit of trial and error and work that out. But I didn't need to find this 14 if I didn't want to. I could just stick with my divisibility rule and that would be enough. Is 4 a factor of 42? Is it true that 42 equals 4 times something, where the something is a natural number, 1, 2, 3, 4, 5, etc.? Well, I can come up here and say, well, if 42 is 4 times something, let's say maybe it's 4 times k, well, that would mean that it would have to be 2 times 2k, right? So if I look at this first 2 here, I can ask, well, is 42 a multiple of 2? Is 42 an even number? Yeah, it is. So I note that 42 is 2 times 21. And kind of matching things up, I see my 2's here. So then I would need to have 21 being equal to 2 times k for some natural number k. In other words, for 42 to be divisible by 4, it needs to be divisible by 2 and then 2 again. So when I take 42 divided by 2, that result needs to be divisible by 2. Is 21 divisible by 2? Well, no, it's not, right? Because it ends in a 1, not a 0, 2, 4, 6, or 8. And in fact, we can verify this by noting that 2 times 10 is 20, 2 times 11 is 22. Consecutive natural numbers that we put in for k have jumped over 21, have skipped 21. So no, actually, 4 is not a factor of 42. 5 would be my next potential factor. Is 5 a factor of 42? Well, I can just rely on my divisibility rule for 5. Does 42 end in a 0 or 5? No, it does not. 5 is not a factor of 42. What about 6? What's the rule for 6? If it's divisible by 2 and 3, and it is divisible by 2, and it is divisible by 3, so yes, by the divisibility rule for 6, divisible by both 2 and 3, 42 is divisible by 6. 6 is a factor of 42. If 6 is a factor of 42, well, 6 times 7 is 42. Now, I might be tempted to keep going, 7, 8, 9. These are all good counting numbers. But notice that if I keep going, what do I get? I get 7 times 6 is 42, but I already have that one, right? So once I get up to a number where, say, 7 times 7 is 49 and 6 times 6 is 36, once I get up to a number where I've kind of where that number times itself has surpassed the number I'm interested in, I basically stop looking, right? So in this case, I got up to the number 7. 7 times itself is that's the first number that surpasses 42. 7 times 7 is 49. So I check it. I don't get anything new. So this is my list of factors. So find all factors of 42. They are 1, 2, 3, 6, and 7. And I circle 7. I also have other factors, right? If I work my way back up the other side, I could ask for these bigger numbers. Is 14 a factor of 42? Is it true that 14 times some natural number is 42? Actually, yes, right? So when I work my way down this side, I only go down to what ends up, we might call this something like the square root of the number. And I see that I've repeated one of my factors here. But if I stopped at, 1, 2, 3, 6, I'd be missing some. I'd be missing like 14, 21, etc. So then I can come back up the other side. I found all of these uh, additional factors by asking, okay, I knew that 3 was a factor of 42. So 3 times what gives me 42? That was 14, 21, and 42. So each time that I identify one of these kind of smaller factors, it's going to be associated with a larger factor. So this is why I don't have to go through 7, 8, 9, all the way down to 40, 41, 42, because I'm really leveraging the work that I've already done in finding these factors. How do I find these factors if the number is bigger and I can't just kind of guess and check? Well, I just do long division. If I know that, 3 is a factor of 42, I know that 42 divided by 3 should give me my other factor by that relationship between multiplication and division. So these were the factors that I found kind of on the original pass through with my divisibility tests. And then these are the kind of matching, almost like, pages in a book factors. 7 times 6 is 42, 14 times 3, 21 times 2, 42 times 1. So let's look at a more challenging one here. Find all factors of 144. So we can start with 1 times 144 equals 144. 2 is 144 divisible by 2. Does it end in a 0, 2, 4, 6, 8? Yes, it does. I could, wait till later to find my matching factor, but I see that I'm going to end up using that. I might as well just do it now. So what's 144 divided by 2? Does 2 go into 1? No. Does 2 go into 14? Yes. 7 times. 7 times 2 is 14. Bring down the 4. 2 goes into 4 twice. So 2 times 72 is 144. Is 3 a factor of 144? Well, I'm not sure, but I investigate 1 plus 4 plus 4, or 9. Is 3 a factor of 9? Yes, it is. So yes, 3 is a factor of 144. What's 144 over 3? Does 3 go into 14? What does 3 go into 1? No. Does 3 go into 14? Yes. 4 threes are 12, leaving me with 2 of these 10s left over. 3 goes into 24 6 times. Not 6 times. 3 goes into 24 8 times. There we go. 0. So 144 has a lot of factors. Is 4 a factor of 144? Is 144 divisible by 4? I guess I could do the divisibility by 4 is divisibility by 2 and then 2 again, right? So 144 I see is 2 times 72. And I know that 72 is an even number as well. It's 2 times some other number. So 144 is 4 times something. And what is K? K is half of 72. We might recognize this as 36, or we might come over here and do, 72 over 2 and get 36 that way. Is 144 divisible by 5? And the answer here is no, because it ends in 4, not a 5 or a 0. So we can cross that one out. What about 6? It's divisible by both 2 and 3, so yes, it is. How do I figure out what should match with 6? 6 times what gives me 144? I could do long division. I also could leverage something like the fact that I know it's divisible by 3. I know it's 3 times 48. And I might recognize 48 as 2 times 24. Or 3 times 2 is 6, using that associative property of multiplication that I can glob that 2 onto the 3 instead of where it was originally kind of on the 24. And I see that 144 is 6 times 24. So I can sometimes leverage previous work. If I didn't see that I could do this trick, I could have done long division, no problem there. Is it divisible by 7? Well, I told you, I said that there is a divisibility rule for 7, but it's kind of tedious and complicated, and this isn't that bad of a problem. Let me give myself a little more space over here for scratch work. So what am I going to do here? I'm just going to divide 144 by 7. If I wanted to, I could do maybe a guess and check. Maybe that would work. This might be a small enough number that you feel comfortable with that. But I could just divide. So this is a third way that we could do it. We could approach the problem. We could just do long division and see what happens. 7 goes into 14 twice. Bring down the 4. Does 7 go into 4? No. 7 goes into 4 0 times. 0 times 7 is 0. So 7 goes into 144 20 times, but with a remainder of 4. 144 divided by 7 doesn't turn out to be a natural number. Or 7 does not go into 144 kind of evenly. So 144 is not divisible by 7. 7 is not a factor of 144. Well, what about 8? Well, if 144 was 8 times k for some number k, different number k than we were looking at before. If 144 is 8 times some natural number, if 8 was a factor of 144, then certainly 144 would have to be 2 times 4 times k, right? Or it would have to be, I could write it as 4 times 2 times k. I could either use my divisibility for 2 here, 2 times 4k, saying that 72 is 4k, is 72 divisible by 4. Or I could use my divisibility by 4, saying that 144, asking is that 4 times something else. I know it's divisible by 4. I know it's that 144 is 4 times 36. I figured that out before. So is it true that 36 equals 2 times k? Or is it true that 36 is divisible by 2? 36 ends in a 6. Yes, this is true. What's 36 divided by 2? 36 is 2 times 18. If I can write my 8 nicer, there we go. So I see that coming all the way back up here, 144 is 8 times 18. Um, that doesn't seem right. What did I do wrong here? Oh no, okay, that's right. When I was multiplying it in my head, I had a arithmetic flub, but all right, looks good. So 18. Yeah, that's good. Okay, so 144 is 8 times 18. Again, we could have just done long division. We could have, if we didn't want to do this trick, we could have taken 144 divided by 8. We'd have got 18 with a remainder of 0. We could have found it that way as well. So there's always a bit of a trade-off between complexity and time spent and so on. This is maybe a more elegant way to do it, is to use some of our previous work, like that we know it's divisible by 2 or 4 or something like that, to use that and leverage that work we had done. But if we don't see that trick, we can always revert back to kind of the standard basic method. Is 144 divisible by 9? Well, being divisible by 9 is kind of like being divisible by 3, then 3 again. So if 144 equals 9k, that's like 3 times 3k. But I know that 144 is divisible by 3. It's 3 times 48. I found that before, so then my question is 48 equal to 3k for some natural number k, 3 times k? Is 48 divisible by 3? Well, 4 plus 8 is 12, which is divisible by 3. So 48 is indeed divisible by 3. 144 is divisible by 9. It's 9 times what? Well, 48 divided by 3, 3 goes into 4 one time. And 3 goes into 18 6 times with a remainder of 0. So 144 has a lot of factors. Most numbers don't have this many factors. But I picked kind of a challenging one to do. I don't know about you, but it always kind of irked me whenever the instructor would do like the easiest problem in class, and then you get to your homework problems and they're like, 3 times as long. So we picked the challenging one to do in class for practice. Is 144 divisible by 10? It doesn't end in a 0, so no, it's not divisible by 10. 10 is not a factor of 144. What about 11? Let's check this one with long division. 11 goes in the 14 one time. Leave me with 3 10s left over. 11 goes in the 34. Well, it goes 3 times. 3 times 11 is 33, but not 4 times. 3 times 11 is 33. Leaves me with a remainder of 1. Since my remainder is not 0, 11 is not a factor of 144. 144 divided by 11 doesn't give me a natural number. So no, it doesn't. And then 12, we actually get 12 times 12 is 144. We know it's divisible by 12 because it's divisible by 4 and also by 3, and 4 times 3 is 12. So if I kept going, 13, 14, 15, 16, 17, 18, I just start repeating these factors going up the right-hand side. So what's my list of all factors of 144? Let me actually write it off to the side here because it's such a long list. I want to keep them all on the screen. So what's the list of all of the factors of 144? It is going down the left side to start. 1, 2, 3, 4, not 5, but 6, 8, 9, 12. And then 12 matches with 12, so it kind of, we don't have to write it again. And then maybe I'll write these going down this way. 144, so we see the pattern. 72, 48, 36, 24, 18, and 16. And kind of in parentheses, 12 is the one that matches with that other 12 up there. So 144 has an awful lot of factors. It's a pretty big number. We had to use a variety of strategies to find all of its factors. Sometimes we just reverted to just long division and seeing if it divides nicely, seeing if we get a remainder of 0. Sometimes we use the divisibility rule. Sometimes we use some of our previous work from previous divisibility rules to help us with future either divisibility rules, like basically yes or no, or figuring out what the other factor was. So again, we can maybe, increase complexity and save ourselves a little bit of time, or we can stick with, doing it kind of over and over with the same approach. We could have done long division for each one of these, but that would have been pretty long and pretty tedious, especially for some of these, like say 5 or 10 that we could knock out immediately without really doing any work. We just know that 144 does not end in a 5 or a 0, so those are immediately out. Okay, let's work on the number 200. And here we, of course, have 1 times 200 is 200. So 1 is always a factor of a number. We have 2 times 100 is 200. I think that's a pretty easy one. What about 3? Well, 200 is a pretty big number. I'm not sure right away, but I do look at the sum of the digits. 2 plus 0 plus 0 is 2, and 2 is not a multiple of 3, so 3 is not. What about 4? So if 200 was a multiple of 4, if 4 is a factor of 200, then 200 has to be 4 times k. But 4 splits into 2 times 2. Or I could group this as 2 times 2k, if I wanted to regroup it that way. But I know that 200 is 2 times 100. So 200 is a multiple of 4. 4 is a factor of 200. If and only if 2k equals 100, or if 100 is a multiple of 2. But 100 is 2 times 50. So I know the 100 is a multiple of 4. Or sorry, 100 is a multiple of 2. 200 is a multiple of 4. In fact, it's 4 times 50. And again, if you didn't want to use this kind of shorter approach, you could have taken 200 and just did long division with 4, and you'd have got 50 out that way as well. Is 200 divisible by 5? Does it end in a 5 or a 0? Yes, it does. So it is a multiple of 5. 200 is 5 times what? I don't have a whole lot to go on here. So let's just do long division. So 200 divided by 5, 5 goes into 24 times. 4 times 5 is 20, leaving me with 0 times left over. I bring down my 0 ones. 5 goes into 0 how many times? 0. 0 times 5 is 0. So 5 times 40 is 200. How about 6? Is it divisible by both 2 and 3? No, it's not divisible by 3. What about 7? Again, the divisibility rule for 7 is pretty complicated. Let's just do long division. See if it divides evenly. See if we get 0 remainder. 7 goes into 20, well, not quite 3 times, because that would be 21. 7 times 3 would be 21. Goes twice. 2 times 7 is 14. Bring down our ones place. 7 goes into 60. Well, this is kind of a tough one. So 7 times 6 is 42. 7 times 7 is 49. Getting closer. 7 times 8 is 56. And 7 times 9 is 63. So 9 is too many. But 7 times 8 gives me 56 with a remainder of 4. 7 is not a factor of 200. When I divide 200 by 7, I get a remainder that's not 0. Is 8 a factor of 200? Well, let's check. So I could kind of leverage what I've done up here. If 8 is a factor of 200, I have to have 200 equals 8k. But this would mean 200 is 4 times 2k. And I know 200 is divisible by 4. 200 is 4 times 50. So I'm using the fact that on one hand, if 200 is divisible by 8, it has to be able to be written as 8 times k for some natural number k, or that's 4 times 2k. And on the other hand, I know that 400 or the 200 is 4 times 50. So just matching up pieces, 2k has got to be 50. Is 50 twice some number? Yeah, 50 is twice 25. So 200 is 8 times 25. What about 9? Well, for us to be divisible by 9, we have to be divisible by 3, then 3 again, right? If 200 was 9 times some natural number we'll call k, that means it's 3 times 3k. It means it would have to be divisible by 3 if it was divisible by 9. But it's not divisible by 3. So it's not divisible by 9 either. Is 200 divisible by 10? Does it end in a 0? Yes, it does. It's 10 times 20, which I think we can see pretty easily. Or if we didn't see that right away, we could always do long division and get 200 divided by 10 is 20. What about 11? Let me erase some of this scratch work over here so I can do this one. 11 goes into 20 one time. How many times does 11 go into 90? Well, 11 times, let's say 8 would be 88, and times 9 would be 99, so only 8 times. We get a remainder of 2. So 11 is not a factor of 200. What about 12? Well, 12 is 4 times 3. So if 200 was divisible by 12, it would have to be divisible by 3 as well, right? If 200 was 12 times k, it would have to be 3 times 4k. It would have to be divisible by 3 as well. But it's not divisible by 3. Therefore, it's not divisible by 12. What about 13? 13 goes into 20 once. 13 goes into 70 how many times? We might have to come off to the side here. So what would 13 times 5 be? 5 times 3 is 15. 5 times 1 is 5, plus 1 is 6. 65, we're almost at 70. If we went up to 13 times 6, we add another 13 on, that would put us too far. So 5 times 13 is 65. And we're left with a remainder of 5. 13 is not a factor of 200. If we look at 14, 14 is 7 times 2. So if 200 was divisible by 14, it'd have to be divisible by both 7 and 2. It's not divisible by 7. So it's not divisible by 14 either. If I go to 15, 15 is 3 times 5. If 200 was divisible by 15, it would have to be divisible by 3. It's not, therefore can't be divisible by 15. What is 15 times 15? 5 times 5 is 25. 5 times 1 is 5, plus 2 is 7. And then for the tens place on the bottom, 1 times 5 is 5. 1 times 1 is 1. So adding these together, I get 5 plus 0 is 5. 7 plus 5 is 12. 15 times 15 is 225, which is bigger than 200. I can stop here. If I kept going, 16, 17, 18, 19, none of those would be factors of 200 until I get up to 20. And then I would just start working my way back up this column. So once I get to a potential factor where that number times itself is bigger than the number I'm looking at, I know I can stop there. And so what are my factors of 200? whoops, not 3, 1, 2, 4, 5, 8, and 10. And then coming back up the other side, 20, 25, 40, 50, 100, and 200. So this is kind of the opening of the book. The 10 matches with the 20. 10 times 20 is 200. The 8 with the 25. The 5 with the 40, and so on. But these are all my factors of 200. So this was another one like 144 with a lot of factors. A little bit of a bigger number. There weren't as many successful factors as 144, so we had to do a little more long division and a little less of the kind of relying on previous work. But we did rely on the non-divisibility of 3 to knock out divisibility of things like 6 and 9 and 12 and 15 really quickly and easily. So being a bigger number, we had to inspect, like, say, divisibility by 13 that we didn't have to do for 144, but we also got to leverage the non-divisibility by 3. So each problem has its kind of pluses and minuses that you can take advantage of. Any questions on any of the material from today? All right, so next class we will talk about prime numbers, prime factorizations, least common multiples, and move on from there. I will see you all on Thursday. Have a good one.
When do we have tests?